quite a long time ago, I was a young man growing up in a small seaside town. And these are the days before you would just went and ordered everything you wanted on the internet. So I used to go along to a little electronics shop that was local, and they mended TVs and also things like arcade games and things like that, Pac-Man and Space Invaders, that sort of thing. And I used to pick up things like scrap boards from them to take apart for parts. And I very clearly remember some very large boards. They're about sort of 14 inch by maybe 9 inch, something like that, all edge connectors, and covered in 7/4 logic. And they were, from one of these video games, Pac-Man or Space Invaders or something of that ilk and that time. And they were covered in 7/4 logic and not a processor to be seen. And, from time to time, I kind of look back upon those days, and I look back to the earlier days when I first did my sort of formal electronics learning. And we learnt about logic gates. And in fact, we learnt about how to construct logic gates from transistors. We learnt how to combine logic gates. We learnt various types of logic and all the maths that goes with it. Often nowadays we tend to forget about some of that when we're designing things and we're using the latest IC off the shelf for £2.50 from DigiKey that does everything but put your washed socks out for you. So I've had a bit of a hankering to get back to some of that old logic for a while, and yet we're going somewhere with this. So I decided that I would do a project, and it will take a little bit of time, and this video is just going to introduce that project, talk about the main principles in it, and then fairly quickly I'll get another video in a series released for you, and we'll work on that. What am I going to build? Well, I'm going to build a computer. That's fairly straightforward. You say just take some bit of logic, Z80, nope. No microprocessor in this computer. This is a 7/4 logic computer built just using, that's it, 7/4 logic. So I'm aiming at around about a 10 megahertz 16-bit computer, which is going to be made from 7/4 logic ICs. So availability is a bit tricky nowadays. So 7/4HC, 7/4HCT and 7/4F are probably the ranges that I'm going to use. And nothing of the kind of very late development stuff. It's all things like AND gates, OR gates. I'll certainly use some bus transceivers and buffers, inverters, that sort of thing, counters of course. But yeah, think of electronics in the 80s. That's the type of technology I'm going to be using. Unfortunately, one or two of the things that were available in the 80s are no longer available. So that's a bit of a drawback. I'll have to actually create some of those myself if I want them. 10 megahertz 16-bit computer. So that's a 16-bit adder, full 16-bit wide registers, and I'm going to give it 16 megabytes of RAM. And my aim is a 10 meg computer, and I want to drive video in particular, because the follow-on project I want to do to this is a 7/4 logic video card. And I'm going to be looking at either 640 by 480 or 1080 by 720 resolution on that card. So I need quite a lot of RAM for that, and that's what's influenced me to go for a 16-bit computer with 16 meg of RAM, because without that capability, driving a video card of that ilk is just not going to happen. So I want video, I want some sound, UART, I want to be able to plug in some ROM cartridges, and I'd like some other I/O and keyboard and stuff like that as well, of course, ultimately. But mainly this project series is going to be about building the computer, and how we build essentially a microprocessor without using FPGAs or any of the modern stuff. We're just going to build it from logic. There are some other videos out there dealing with similar topics, and I've taken some of my inspiration from them, and there are some things that are going to be very similar in my build to theirs, and part of that is just because if you want to build a register, there's not too many choices about how you go about that, really. You might choose one component over another, but generally speaking, the principle is going to be the same. How you plug that together into your wider circuit, of course, is a very different matter. A few highlights, I guess. So I am going to focus not just on the technical content, but on the actual sort of approach, and I use a very iterative approach. So this slide pack that we're looking at the moment, for example, is kind of like my scrapbook, really. So here's the 16-bit registers in an architectural setting, and some other registers down here, and here's a bit more detail on 16-bit registers. And I've left this long enough to get a good feel for how to do certain things before launching the project. But yeah, I go from this to I've got an Excel spreadsheet just here, and in this I've got some of the opcodes that I think that I'm going to want to use. And what I'm doing really is I'll look at my architecture, think, oh, I think I might need to alter that a bit. I alter that, then I come back to this and say, what does that support? These instructions. And then I think, oh, hang on a minute, I need an instruction like a these are all ands and ors and nots. So there we go. I need a compare instruction. I need to be able to compare two numbers, see which is biggest. I need to be able to jump conditionally depending upon the outcome of the last piece of maths. So start thinking about those instructions and start thinking about whether or not my little scrapbook diagrams actually support that happening. Can I, so these lines here, so this is a register, this is a line between the register and a bus, you know, if I turn that on and I turn a combination of these on, can I make the computation happen that I want to happen? So doing that quite a lot. Also begins to firm up a little bit. I like to switch across to simulation, and I tend to use simulation rather than creating large amounts of stuff on breadboard. Although I will use breadboard from time to time. But anyway, here we go. This is actually part of a general purpose register on the screen at the moment. So what I've done is I've in simulation built a single register, and what that's done is it's firmed up for me all the control lines that I need to come from the decoder unit. It's also helped me get a feeling for the scale. This is a full 16-bit register, and it's got all of its connections through to the different things that are on my scrapbook. So if I look at my scrapbook, here's a 16-bit register, register A. It connects to the right-hand side of the ALU, the left-hand side of the ALU. Those are two inputs for the arithmetic logic unit, and the result of the ALU, and also an internal 24-bit register bus just here, as well as to the actual data lines going to the user memory. So yeah, so that's quite a lot. How does that look when I put that into an actual thing? What's my device count? How do I clock my data in and out correctly with proper timing so that it doesn't all end up in a mess? And yeah, you can see over here on the right hand side there's some wires that I've put in there that I'm not using because I realised I'd made a mistake and disconnected those. And up at the top there's a bit of logic that I hadn't expected to be putting in, but yeah, it was needed. So there we go. So yeah, so I can actually run this simulator up. Transient analysis, thank you very much. We run that and we can see a timing diagram on the left hand side, and we can see some actual data on one of the data buses. Now this is connected through to the arithmetic logic unit, which is only 8 bits, which is why only 8 bits of data are showing. But anyway, there we go. So that's quite handy. And yeah, over here we've got the actual ALU. Also running in simulation simultaneously with that. And on the left hand side, for example, I can look and I can say, here's my first ALU coming out. That's the last piece of the result on 0, I think. We can magnify that up. Let's just go there. There we go. And put the cursor back on. Yeah, and I can see the very, very final piece of calculation finishes at 28.2 nanoseconds after we start the instruction. So that's pretty good. So not quite sure what speed clock that supports, but certainly I've got a 10 megahertz clock running all of this at the moment in simulation, and I've got plenty of headroom on that. Yep, and over here we're actually getting that result clocking into the carry flag, which we can see down at the bottom. So excellent, yeah. So using this sort of technique, I can just refine my decisions on the various parts that are in my scrapbook, so to speak. So yeah. So I look at that. I come up with a rough picture of a 16-bit GPR, general purpose register, and then I go across to the simulator and I firm that up a little bit. And then I come back to my scrapbook and make some notes. And yeah, here's the ALU. You see there's stacks of notes around this now because I spent a long time doing the simulation on this. I've got all of the flags that relate to it. I've got the adder. I've got the shifts. I've got the logical stuff. I've got all the demux settings that the controller needs to know about. Absolutely everything is in here. There's even some examples of how we'll manage the control lines down the left hand side here. And we've got a big smile saying, I think I finished. Okay. So, and further down we've got some examples where how will I do a 30-bit 2-bit subtract using this architecture? I'll do it like this. It works. 2 cycles. Okay. So there we go. So back to the approach again. So another piece that, so we've got simulation. I do prototype a few bits. If I'm a bit doubtful about them, I can put them onto board. But you know, the simulation is good enough for a lot of stuff. Yeah, circuit and PCB design. In particular on this one, there's a problem with the amount of lines that run around. I want to make this using a modular technique, and that means a backplane, and I'm going to plug in the boards. So I'll build 1 or 2 boards for the general purpose register, for example, and they need to plug into a backplane. That means a big connector. Okay, how big? Well, I've chosen the PCIe connector. That's 164 connections. And I certainly can't just push all of the internal connections of the processor through that 164. It's nothing like enough. But I can push all the connections in that I need for the 16-bit register, I think, and I'll need a slightly different version of it for a 60 for the things like the program counter and index registers and counters and things like that. So if we go across to Circuit Studio, we can kind of see what I'm doing there. So here was I was just putting the clock circuit on one just to see how it looked, and I made a few decisions about that. So this is a PCIe card. So it's the type that would fit in a computer. I decided that wasn't any good. So what I'm actually going to do with this, and I'm going to extend it upwards a bit. It's 161 millimeters wide, I think, by 111 or 117 high. So I'm going to extend it upwards a little bit, so it's about 160 by 160 millimeters. And this bracket, which is a PC bracket, I'm going to take off, and I'm just going to put a flat bracket with 2 screw mounting holes along the top. And that will mean it can actually slot into, can turn on its side. Yeah, I can't do that very easily. It will turn on its side and actually then slot into a back plane and just screw in with 2 screws to tighten it into place. That will be a lot easier than messing around with like a PC subframe to put it into. So so that's great. If I come down here, is this the right place? Who knows? Yep. So here's my edge connector. So this is a component in Altium, and I have a similar component which is just the connectors without anything connected to it. What I'm going to do is I'm going to create another version of this component and pre-connect a lot of these connectors to their nets. So for example, they all need access to power, so that will be connected. They all need access to the internal 24-bit bus, so I will put that on these early connectors. They all need access to certain control flags. So again, I'll pre-connect those up, and then I'll save that as a sort of 16-bit register version. And then I'll create another version which is for the, let's say, the 24-bit registers for counters and things like that. And perhaps another version for the ALU or whatever. So 2 or 3 versions of these all pre-populated. And I'll give it alternative footprints. So here's one footprint, which is a card edge. I'll then give it the corresponding female connector that goes on the back plane. Will be another version of the PCB component. And that will mean I can just actually drop these onto the back plane, onto the edge of panels and so on, and I can be sure that I have the right connector set and that everything actually corresponds between the back plane and the circuit. So a bit of thought about that sort of thing, and just seeing the boards early on does actually help. So here's the board, a bare board, and this can be saved as a template. So this all helps just get everything lined up, get a feel for how much can I fit on here. You know, okay, I could fit 1 register on it easily, but can I fit 6? I don't think so, but I can probably fit 6 on 2 of them. And if I make them a certain spacing apart, then I could actually put a kind of interconnect on the top, and I can have a double depth connector. So yeah, you know, we can think those things through because of the approach that I'm taking, this sort of iterative approach going backwards and forwards. And it might well be one of the questions I got with my design for the 16-bit register. Yep, if I just zoom out on that a little bit. So one of the questions I've got on here is that I've got it connecting directly to the RAM, to the RAM data lines. So it can read directly from RAM and it can write back directly to RAM without using any of the interim buses within the processor. That's kind of a luxury. I don't necessarily need that. I can do the same thing via a different route. It's just that on very rare occasions there might be contention for 2 things wanting to use, let's say, the internal bus. So yeah, that's not that's a decision that I need to sort of make still. And in actual fact, as I start to populate these onto the board, if, let's say, for example, I can get 2 of them on the board and I need 3 boards, but if I take away those program connections, I can get 3 on a board and I only need 2, then yeah, I'll probably go that way. You know, so cost and logistics on the PCB might actually alter how I do 1 or 2 things. Now, if I take those away, then the program microcode that I use in order to actually drive all of this from the processor decode unit is going to change as a result. So there's a little bit of this is why we're kind of iterating through it all the time, trying to make those decisions. Now, the last thing that I also like to do fairly early on is to actually start writing the manual. So here we go, programming the MOR processor, assembly language by me, there's some instructions, and here we go, starting to get the main bits and pieces in that we need. Some stuff about, notes about how I'm going to write the assembler, notes about the assembler itself, how would I expect things to be appearing there, constants, data origins. Oh, hang on a minute, I'm using a different architecture, so you know, how do I show where code is, how do I show where data is? Okay, how is that going to translate into code for my processor? What about literal representations, indirect jumps? Oops, hang on a minute, I need indirection. That's tricky. So yeah, I need indexes, I need block moves, I need to do all sorts of things. I need to decide how I'm going to lay out my operands. Are there any things that I need to encode within those? Actually writing the instructions does help me begin to understand that. Here's an add with carry instruction. I've said it takes 2 cycles. In fact, it only takes 1. That's great. What flags does it affect? Yeah, 0, carry. And here I'm saying that I will indicate if bit 15 is set. Well, I'm not going to do that anymore. I've designed my ALU and it doesn't actually do that. So essentially on an add, we've got 0 and carry. There's not really a lot else to do. And here's an add without carry. Just get rid of that. It's only one cycle. Anyway, I'm not going to write it now. So, so it's useful just to drop backwards and forwards with those, and kind of all the time I've got in mind what my sort of ethos for this is, the 7/4 logic type approach. I've got my target speed, 10 megahertz, you know, so I'm pulling out technical data. What opcodes can I support? What are the if we go down to the ALU diagram, what are the various control signals? Well, I've got a carry and select. You can go from 0 to 5. I've got a carry source select. You can go from 0 to 4. I've got a 0 source selection. You can go from 0 to 3. I've got a source carry out. If I go to the diagram, then I'll find that I've got some other things like there's a single control line that says I am carrying out an ALU. It's over here. ALU flag load, ALU sub. So I am performing an ALU instruction on this cycle, and I want you to store the flag for future use. And the other one means I am doing a subtraction type activity. So I want you to decode the carry that comes out from the adder chips, so that you can actually work out whether it's a borrow or a carry. So yeah, all of that comes from going through this iterative process. And if we weren't thinking about, you know, so over here on the left hand side, you know, how do I do a subtraction using this architecture? How do I do a comparison? How do I decrement the value of a register? How do I increment it? How do I clear it? Going across to flags, how do I clear my carry flag? You know, until we start sort of thinking of scenarios of usage, until we start thinking about the instruction manual, until we start thinking about the opcodes and the assembler, then actually it becomes really, really difficult to finish the actual designs. So just got to go backwards, round and round in circles a little bit. And there comes a point inevitably where you think, I don't know if I'm really getting anywhere with this. And then you get past that point and actually things start pulling into line as your thinking becomes clearer. But yeah, I would strongly recommend for larger projects that you pull together some sort of general overview document that you kind of keep updating in parallel. Just keep going around between them. I've done a lot with computer programming. There's a lot of tools that enable you to do that sort of automatically, but yeah, I don't really use those now. I'm not working properly, just doing things that I enjoy. So anyway, let's take a quick preview of the process that I'm going to make, and then we'll finish this video and move on to actually I'm going to start with I think the 16-bit registers, but I'll go and look at the picture of a processor and just talk through what videos are coming up. But here we go, 7/4 series 5-volt logic. I might vary a little bit when we get to things like the sound card, for example. Maybe I'll use some programmable logic in there just to simplify it, and maybe for the UART I might just use a plug-in UART, because truthfully by the time I built the processor with 400 ICs or whatever, I'm kind of gonna probably got tired of just building stuff out of logic. 16-bit, 16 meg. I'm using Harvard architecture, so that means I have separate user data areas and program store. So 16 meg for each. I've said here at least 4 16-bit general purpose registers. I think I'm going to have 6. It should have a symmetric instruction set. So you know, if for example you can add A and B, then you can add B and C and D and E and A and D, and you can subtract them, and you can kind of do everything that you can do with every combination of registers, really is what we're saying there. There'll be some other registers as well. At the moment I've designed in 3 24-bit registers, and they are a counter and two which I've called source index and destination index, although they don't have to be used for that purpose. But the idea is that you quite often need to move blocks of data from one place to another, and for that you need a source, you need a destination, and you need a counter to make sure you only move the right amount of stuff. And that's pretty common stuff. So I've put those in as registers ready to go. I am contemplating, when I get to the decoder, actually enabling it to do that 100% in hardware without having to cycle back through the program. But we'll see. It might prove to be more complicated than I'm willing to go. ALU, obviously we have to add, subtract. Can we do it in one cycle? Yes, we can, is the answer. I want to maximize one cycle instructions. Some things will be 2 cycles: jumps, indirect addresses, conditional instructions, and things like that. I like it to take 2 cycles. There's nothing I can do about that. I was thinking about making a pipelined processor. So this is where you start one instruction, then you go and get the next one, and then you start the second instruction while the first one is still going. Then you start the third instruction while the second one is still going, and so on. If I've got a lot of one cycle instructions and a Harvard architecture, then I don't get that much from that. The pipeline really helps when your data bus is going to be tied up, because you can kind of prefetch stuff and it's all there and it's still going despite the fact that you are using the resources that you need. With Harvard, you don't have quite so much contention, so that isn't quite so important. And if they are one cycle instructions, then actually you don't get anything out of a pipeline, because the whole point of the pipeline is that you have, an instruction that takes 4 clock cycles can have another instruction running at the same time, and that can have another instruction running at the same time. With one cycle instructions, you never have that. But even if I decide not to go for a pipeline, then I will go for prefetching. So this is where you start an instruction and you immediately go and get the next one in readiness. And one of the reasons for that is that as I've started thinking about the process of decoding an instruction, I realise it's going to be very slow, and the reason for that is actually the last of the reasons on here, last of the points on here, which is that it's going to use a microcode instruction set. So I'm not going to hard code all the instruction logic. What will happen is it will read an instruction from memory, and then it will look up all of the control signals that it has to output to the rest of the circuit to execute that instruction. And that will be overwritable, so that I don't have to kind of do all of the instructions all at once. I can actually just build 5 or 6 instructions in, and then once I've got those working, I can kind of just move on and evolve further instructions and start adding them in, and then at the end I can come back and round it all off and make it a complete instruction set. Working from bottom to top, there's an implication for the assembler there, which is that the assembler and the microcode instructions, what the processor does, are intimately connected to one another. So I'm going to produce a single piece of software that will enable me to put in microcode instructions and the opcode that goes with it, and the assembler will automatically understand those and be able to produce the code. I haven't yet given full thought to how interrupts are going to be supported, but they will have to be supported. What else have we got? Relative and absolute jumps, that's absolutely fine. How do we push and pop 24-bit registered in 16-bit memory? That's an interesting question. It kind of goes on with how do I do a call. So for a call, we have to push the program counter into memory, and then when we've finished with our subroutine, we have to pop that program counter back out. Now the program counter is 24 bits wide, so it's the same problem. How do I get that 24 bits and then make my jump all in 1 or 2 clock cycles? Got to think about that. I'd perhaps like a separate I/O port address, and there is a question: shall I have a separate I/O port in its own right, or shall I just share that with the data? I'm not quite sure. So there's a fair bit of work left to do. But at least that perhaps gives you a feel for what the processor is going to be like. In terms of the next releases, I've done plenty of work on the general purpose register, so I'm probably going to, and that kind of has to be early, because how can I test the instruction decoding if I haven't got any registers to move stuff in and out of? That's the single most fundamental thing that we do in a computer. So I kind of need that register there, or I need some 16-bit. So I need some registers of some type to move data around with. I'm quite progressed with the ALU, so I might also go ahead with that and do another video on the ALU specifically, because it kind of ties in with the registers a bit. My decisions on how to build the register were predicated by decisions I took around the ALU, and vice versa. And certainly in terms of the overall architecture, how many buses have we got in here moving data from one place to another, that was also predicated by the ALU and the general purpose register in combination. So I'm probably going to do fairly early a video on the general purpose register, a video on the ALU, and excuse me, and then I'll probably take a first view of the decoder and instruction register and program counter, and then start to insert some of the 24-bit registers, index registers, and things like that in place. There'll be a register in here which is which I call literal value, which is when you do, for example, jump to address, whatever, then that's actually a two-word instruction in the program memory, and we need to load that second word is a piece of data that we need to use. So that actually has to have a temporary register that it can be stored in. So so that's, I think, where we're going to start. And once we've got that sort of pretty much running, then we can turn our attention to the memory, and finalize up the clock circuit, because I'll just run this on a simple external clock for the time being, and start fine-tuning stuff like the performance. I think the decoder is going to be very, very tricky to maintain the performance that we want. Okay, so that's pretty much it, I guess. So if you're interested in seeing the rest of this series and the various builds, then please click on the little subscribe, obviously, and click on the little notify icon. I think it's a bell in YouTube, and I'm not quite sure what it is in Lbry or Odysee. I think it's a bell as well. But yeah, click up to be notified, and then you'll see the videos arriving. There might be ones you're particularly interested in, ones that you're not interested in. That's absolutely fine. It's entirely up to you. But yeah, they will take quite a while to come out. I think the general purpose register one will come out fairly quickly. But at least in terms of the design, in terms of making the board and populating it and plugging it in and testing it, that will be a video on its own right. So yeah, I kind of expect, I don't know, maybe 20 videos in total in the series, spanning about, I'm going to guess 5 months, something like that. And that will get me to a workable processor and computer that I'm then willing to move on to some of the other sub things like the video and the UART. I will be initially, I think, as well, using a temporary memory system, because until I've actually got a working computer with a working operating system, I've got no means to load programs dynamically. So my thought is that I will have RAM for both program and data, and that I will have a little plug-in ROM that will copy itself into the RAM at startup, and that will be how I load the operating system, and probably that's how the operating system will load permanently. Ultimately, of course, that ROM will only contain the operating system, but for the time being, it will have to contain the various test programs that we need in order to prove everything works. So anyway, what have I missed? Anything at all? Okay, so if you like this, if you like the concept, please tick like, please subscribe, please remember the notify button. If you've got an insight into making your own processor, if you've done it yourself, why not put some details in the comments down below, put some links in. And in the meantime, I will also be doing lots and lots of other videos. For example, the doorbell rang earlier, and it had a nickel plating kit in there, so I'll be giving that a go shortly. I'm posting a video in the next day or two. So take care, see you next time.